Good afternoon all. I am Geetanjali Chandam and today I'm going to present our study which is monitoring buildability of 3D PC using ultrasonic guided waves, and this work was guided by Professor John Popovics and my advisor Professor Myung-Soo Sin. And this is the overview of my presentation, and under introduction we are going to briefly go through what I will be discussing in my study and introducing a little bit on what are guided waves. And under test methodology, we are going to discuss on materials and mix design, early edge material properties, printability of the mix design, and also a little bit about the ultrasonic test setup, grain strength test, and we will discuss test results on attenuation, grain strength, and the correlations between them. So first, the main motive for our studies, which is monitoring 3D PC in the early printing stage. So when we print the this kind of concrete layer by layer, there tends to be some kind of failure in between. So we would like to send signals through this fresh state so that we want to monitor such kind of failure. But it is quite difficult to send signals in concrete during its fresh state, so we thought that maybe a guided wave might work. So our idea was to attach a waveguide on the specimen and then send the wave will propagate on the waveguide, not on the material. So after our study will be concentrated on the energy leakage from a waveguide to the specimen. And so with this, we have the entity parameter. So from that entity parameter, we can predict our strength. And overall, we might have a control system where we have to print or where we have to stop our 3D printing. And so moving on, so I will introduce briefly what are guided waves. So guided waves are waves propagating in very thin or finite boundary. And guided waves can be propagated on cylindrical or plate-like structures. And in cylindrical, guided waves are divided into longitudinal, torsional, and flexural. And on plates, they are called Lamb waves and divided into symmetric and antisymmetric waves. So these are formed by superposition of P and S waves. So this is what guided waves are, and we are going to apply this to our monitoring system. And the materials and mix design. So the variables for our study is the fiber, which is of 5 millimeter and 2 millimeter length. And why we choose this kind of variable, it is because we are known that 3D PC might subject to shrinkage, and our previous study have proved that using this kind of materials improve the shrinkage of the concrete materials. So which is why we aim to use this as a variable for our study. And the content is fiber content is buried up to 2% for each length. And moreover, we can see the SEM images for these fibers, and we see there are pores inside the fibers which help with high absorbing water capacity and acts as an internal curing agent. And this is the material early edge properties, and this initial setting time increases with the content and the amount of fiber, with the content and the length of fiber. However, the flow decreases over time. This may be due to the incorporation of fiber reducing the flow of our materials. And this is a brief overview of the printability of the mix design. And I will not be discussing deeply in this, but I would like to show that the materials we propose here are printable, and they have a build-up height of around layers ranging between 15 to 19, with each layer height of 15 millimeter. And this is shown from CF00, which is no fibers until 5 millimeter with 2% content. And next setup, it is the ultrasonic test setup, and we can see that this is the waveguide, and the orange color is the waveguide, and we are going to attach our sensor on the waveguide, and we are going to send the signals here in a shear wave mode, so that it will leak in this kind of in-plane motion mode. And another thing is we have chosen two different kinds of waveguide, which is aluminum and acrylic, because I will further talk about in the next slide. And then the one on the far right, it is the input. It is the details about the input signal. And why we have chosen two waveguides? It is because of the material properties, and during concrete in its very early stage, they have material properties, or like the density is quite less and so on. We would like to choose a material which has close property with the specimen. And moreover, these are called dispersion curves, and we are going to find out how the wave behaves at certain frequency, which is why it is drawn for the aluminum and then the plexiglass. And we have to pick certain point of frequency which we will excite in these waveguides, and which is why I have shown here 3 modes at 60 kHz frequency and 5 modes at 100 kHz frequency. And this is the test results from using the aluminum waveguide. So we can see from the test result itself, there is less sensitivity using, when we use aluminum waveguide. It is because their material between the specimen and the aluminum waveguide is still different, and there is very less energy leakage from aluminum to the specimen. So which is why we see that over time, which is one is in the frequency domain, one is in the time domain, and we can see the energy loss cannot be seen. So it is we say it is less sensitive, and we are not discussing about aluminum waveguide further. And next, moving on, we have the acrylic waveguide with 60 kHz center frequency. And you can see from the graphs here in the frequency domain that there is some point of energy, decreasing of energy over time from 15 to 120 minutes. And I forgot to mention, we did this test for 2 hours right after casting. So this is called, from here we can find out a parameter called attenuation using our initial amplitude at 15 minutes and the final amplitude at around 120 and 30 to 120 minutes. So this is some arrival time of S0 mode, which is derived from the energy velocity dispersion curve. So looking at the test result with 100 kHz center frequency, we can still see that there is kind of decrease in wave spectral energy if you look at the frequency domain over time. So still in 60 kHz and 100 kHz, there is wave energy decrease. And this is to show about what kind of modes are coming here. And from the dispersion curve again, we can distinguish this might be the arrival time of S0 mode, but we cannot partially differentiate them. And moving on, this is our test result. The attenuation calculated from the first amplitude and those amplitude afterwards. And we can see that regardless of the test variables, attenuation increases with curing time. That means that as hydration continues, we know that the specimens are stiffening over time. So at this point, the waveguides moving in the acrylic are leaking towards the specimen on the stiffening specimen. So that is why we see higher attenuation over time. And moreover, with the addition of 2 millimeter or 5 millimeter fibers, there is some amount of attenuation is lesser. This is due to the fact that addition of CMF leads to hydration delay for cement-based materials because of internal curing effect, which is why we see lesser attenuation with addition of fibers. And similarly, with the 100 kHz center frequency, we can see attenuation increase over time. But if we have to compare between the 60 kHz and 100 kHz, 100 kHz have higher attenuation. This is because in this frequency range, the wavelengths are smaller if we have to compare to 60 kHz. So because of that, there is finer wave propagating inside, and hence there is more leakage from the waveguide to the acrylic. So others are similar to the test result we see from 60 kHz. And the next test is the grain strength test. It is the compressive test we do, but we call it green strength because it is conducted in a very early age, which is less than 2 hours. The materials is still in the fresh state. And we did 3 batches of, for all the cases, and then we do the loading, uniaxial loading, at a loading rate of 2 millimeter per minute, which is quite less, but it was conducted for since it is in the fresh state. And you can see that these are the like photographs taken at a displacement of 20 millimeter, and you can see with the addition of fibers, there seems to be the bridging property of the cracks over time if we have to compare the like figures at each point of time. And this is with addition of 5 millimeter fiber. Here even we can see that the cracks are, the CMF had this kind of bridging properties. If we have to look all for, compare the signals, compare the samples for all the curing time. And this is the green strength we have. And why we were doing this kind of green strength or the mechanical property at this early stage, because with this green strength we can predict the number of buildable layer using the some equation here. So there will be, when we print the layer, there will be some pressure exerting from the printed layers above. So if we have to, if we have a known number of layers at some point, and we have the green strength test value, we can see that, okay, this height is still printable, or we have to stop printing at this point of time. So which is why we develop the green strength, determine the green strength test. And if we have to look at the green strength increases with the addition of fibers. As we can see from the previous test results shown, there is the bridging effect from the addition of fibers, which may be the effect that the green strength increases with the amount of fiber. And the next slide is the correlation between the green strength and the attenuation parameter. So if we have an entity parameter which we can develop a relation with the green strength, we can determine green strength at some point of time while we do the printing. We can see that there is a good correlation with 60 kilohertz center frequency when we excite signals at 60 kilohertz. So this is and it differentiates for different fiber content given the inverse relation we see from attenuation and green strength. So if we have this kind of equation or formula, we can predict green strength. And finally, I would like to say a little bit about the inline application about our test setup. So you can see the waveguide attached at the lower layers of the printed concrete, and then we monitor this kind of signals which I explained earlier until 2 hours, and we can see that the bonding between the acrylic and also the cement materials. And this is the test result we have. So the test results from the previous slides which I presented was from cast specimens, and this was from printed specimen. And from printed we have good amount of attenuation, and we can still correlate these with the green strength. And moving on, so I would like to conclude here that we somehow predict, we have the entity parameter which can predict the green strength at some point of time, and with this we can have we can say whether our printing will start or stop and should wait for some point of time. So this study conducted the effectiveness of guided wave to monitor the buildability of 3D PC, and acrylic is found to be more effective given the material property at this age, which means that acrylic was compared to aluminum waveguide, and it was found to be more effective. And there is correlation between green strength and attenuation, and from this we can develop some number of buildable layer which indirectly printed through the guided wave technique. And I would like to acknowledge my lab members which helped me through the experimental process, and that's the end of my presentation. Thank you.